Oh, wonderful. Okay. Yeah, so hello everybody and welcome to my presentation on the topic of automated shotcrete 3D printing and printing interruption for extended component complexity. Let's just first introduce myself. Well, I'm Lukas Lachmayer from the Institute of Assembly Technology in Hanover, and I was closely cooperating with my colleague Dörrie from the ITE at TU Braunschweig for this paper. And both of us, we are part of the TRR 277 DFG-funded project focusing on the additive manufacturing construction. Just check how can this one. Okay, so let me now give you a brief overview of what we are dealing with in specific. So our process is called usually shotcrete 3D printing, and we are using a conventional shotcrete method for layer-wise material application. It can be obtained in the left picture that this process enables us to generate much more complex components than with standard extrusion processes, since we're able to reorientate the nozzle fully and spray nearly horizontally. And due to these capabilities of the process, we have an enhanced design freedom, which can be used to produce, for example, force flow optimized components. I brought one example of such design in the middle, in the right picture. However, with those increasing component complexity, we came across the challenge that we need to realize more complex printing paths and thereby fully control the material application to ensure the component quality in the end. So what I show here in the right picture is a simple example of the force flow optimized capital in the middle picture. And it can be obtained that we need to pass through the middle of the component for several times. And yeah, we came up with the problem that we need to shut down and reactivate the material flow. Sorry. And so if we're not able to interrupt the printing process precisely, we cannot guarantee the component quality because the material will build up in the middle. Yeah, then we took a close look to how those printing interruptions are realized within common processes, such for the FDM process, which is usually uses a multitude of multiple paths to realize complex components. So here in the picture, we can see, for example, sliced boat, where we can obtain by the different colors that we have multiple paths with which are combined to one path in the end by transition movements without material applications. So for us, the question arises, how can we interrupt our shotcrete process without applying material to the gap and thereby deal with the system inertia and also prevent nozzle clogging, which will be caused by curing of the material within the hose. And therefore, to investigate those interruptions, we conducted experiments at the DBFL, the Digital Building Fabrication Laboratory at the TU Braunschweig, which is managed by the ITE and my colleague. And the setup consists of a 9 degree of freedom production robot, which is divided into 2 parts. So a 3 DOF portal and a 6-axis industrial robot. And on the upper right picture, we can see that we have some valves at the end effector. And within this picture, we can see that we usually mix the material in the pump, which is about 25 meters away from the printing process itself, and then the material is pumped through hoses to the end effector. So we have at least 2 parameters, the pump activation and deactivation, and the valve opening status to control the material application. We have on this picture a small scheme of how we conducted our experiments. So we have the X stop, the stop point where we want to interrupt the material application, and X start. And we then added delta T's to perform the closing of the pinch valve and the shutdown of the pump prior to the desired stop point. And Prior to X start, we are reopening the valve and reactivating the pump to compensate for the system inertia. And then we use the DOE to set those parameters in time. For example, in here we can see the time in milliseconds, and according to our path planning algorithm and how we are performing experiments, we had to calculate distances to match the desired shutdown points, or to fit the desired shutdown and reactivation points into the printing path itself. And then, yeah, we have here the scheme of the printing path that we used. So we combined all our experiments into one single path to ensure the same material quality. And then we performed a visual inspection, and we can see here that from experiment 1 to experiment 7, we have a clear difference of the amount of applied material within the gap. So the gap is marked by the white dotted lines. And yeah, for experiment 7, we already by visual inspection can see that there is less material within the gap. However, for a more detailed investigation, we used a 2D laser scanner and performed scanning of the samples. And within those scans, we defined the start point of the specimen, the end point by the transition areas, and then could calculate where X start and X stop, so the desired start and stop points should be. And then we defined 4 areas: post-start, pre-start, post-stop, pre-stop. And we stated that within the pre-stop area, we want a higher amount of material within the gap. So post-stop and pre-start, we want at least near close to no material. And in post-start, we want the highest amount of material, similar to pre-stop process. And yeah, we then were able to calculate the volume of material based on those scans. And I have here the graphs. A and B are according to the printing interruption, where we can see that our delay time of delta T stop nearly has no influence on the pre-stop area up to 1 second. However, the amount of material behind the desired stop point is reduced by increasing the delay time. So for our further experiments, we set the delta T stop to 1 second, and the evaluation of the reactivation of the material flow was a little more complex, because we can see we want in pre-start the minimum and post-start the maximum, and those 2 points don't match each other. So we divided the amount of material and could find the optimum. And for our further experiments, we then had the shutdown process delay by 1 millisecond or 1,000 milliseconds. And for the restart process, we choose 250 milliseconds for the valve opening and 2,000 milliseconds for the pump reactivation. So we first start the pump to build up pressure and then open the valve. And we then use these parameters to perform the printing of the initial component I showed. So the bottom part of the capital, in the left side, the CAD file and the printing path. On the right side, a picture of the final component as printed. To get a better understanding of how the printing was performed, I also brought a little video. We have here the usual printing process. Then we have the printing interruption, where we shut down the pump and the valve, the transition area, and then we are having those 1 second of delay, where we reactivate the process and then continue the printing. It can be seen that we are definitely reducing the amount of material sprayed within the gap, and that we have a very good timing of the restart process. However, there can be done a little improvement according to the shutdown process, because we still have some material left within the gap, but this will be done in a further experiment. However, overall, we were able to interrupt the printing process, which enables us, especially for the shotcrete printing process, to compensate the system inertia generated through the material pumping through the hose, and thereby enhance the complexity of components that we can build. Yeah, that's it for my presentation, and I'm open for your questions.